Hello. In our series on application of derivatives, today we will talk about word problems of maxima minima, one of the most important applications where the situation is described in words and you need to maximize or minimize volume, areas, costs depending on what is given, known and what is varying. It is best understood by looking at one or two of the standard questions which you need to master. Once you have understood a few of them, you would realize that the underlying procedure is the same in all of them, but you need to understand and interpret the given and unknown in the required manner. We will start with one of the regular, most standard and of course, if you are one of the CBSE students, then one of the very favorite of the CBSE exam as well, a question known as a box problem. The statement is long, but it is one of the questions from your NCERT textbook. So, let us see if you can keep up with it. The statement says, a rectangular sheet of tin of 45 centimeter by 24 centimeter is to be made into a box without top by cutting off squares from corners and folding up the flaps. What should be the side of the square to be cut off so that the volume of the box is maximum possible? Now, this is one of the activities that you can always try with the paper. Take a rectangular sheet of paper and try to cut off squares from the four corners. You will realize that you can do that in different ways. The side of the square that is getting cut off can vary. And when you fold up the flaps, the net that you get, it would result in a box of different volumes. We want to find that box which has the maximum volume. Let me show this to you with the help of a dynamic model. Here we have, for representation's sake, let us consider a sheet of length 4 units, width 6 units, and we are going to cut squares from all the four corners. That can be represented by this H, which if I change, you see those dashed lines changing? So, these squares are getting cut off, which would result in the four flaps which are going to be folded to result in a box. I am going to just tilt this sheet around so that you get a good representation of the box that is getting formed. See how the box folds up, and this is what you would get in different sizes depending on how many units of square you have cut off from the four corners. So, if I take H to be 1.54, then the box that I have got will have a volume different from the volume of the box with the height of say 1.09 or 0.87. Now, we have to figure out which of them gives us the maximum volume. The volume of a box is nothing but given by length into breadth into height, right? So, that is the function that we are going to be maximizing. In this case, it is 4 minus 2h. Let me bring this down so that you can see it clearly. 4 minus 2h into 6 minus 2h into h. So, as h changes, this is changing. Which one of them is maximum? 8.29 or 7.95 is what I need to figure out. In this case, you can definitely see that there will be some point at which the height will be such that the volume is maximum, not necessarily when the height is maximum. We can see the same thing through the graph. If I plot the graph of this function, let us take a look at this picture. When can we see the volume to be maximum? As we have discussed in our previous lessons, the volume will be maximum at the peak, that is where you have the maximum point here. In this case, which is that maximum point is what we need to talk about. Obviously, that will be the one where we have the derivative vanishing. Obviously, right now what you are seeing is not the entire of the function, simply because being a cubic function, it will not only be a parabola, it is actually a big function which is going up and down. You can't see that very well in the screen. Now, this is what we need to do algebraically. We want to get this volume function and then maximize it using the first or the second derivative test. So, let us get back to the algebraic solution, starting with an understanding of what you have and what you do not. In this case, we want to cut off squares from the corner and we do not know the dimension of that square. So, let x centimeter be the side of the square which is to be cut off from each corner. That means the dimension of the box are 45 minus 2x, 24 minus 2x and x centimeter. 2x because from both the sides the box of square of x unit length has been cut off. So, 2x units have been taken off from length and breadth, and the height, as you saw earlier, was the same as the side of the square cut off, that is x. So, the volume of the box L into B into H is a cubic function, resulting as 4x cube minus 138 x square plus 1080 times x. Find the derivative, because we are going to use the derivatives to find the point of maxima and minima. In this case, derivative turns out to be a quadratic, which is going to be maxima minima when it is 0, resulting in two values of x is 5 or x is 18. Now, x equal to 18, is that a possible value? No. Why? Because when the value of x is 18, breadth becomes less than 0, not a possibility. So, we reject or neglect x as 18 and concentrate on x equal to 5. Is x equal to 5 a point of maxima or minima? Can be decided by second derivative. Second derivative is 24x minus 276. At x is equal to 5, it is a negative quantity, less than 0. Second derivative implies, that is second derivative test, implies that volume, that is V function, is maximum when x is 5. We are interested in finding the side of square to be cut off from each corner, then that side has to be 5, so that the volume is maximum. If you want to find also the maximum volume, then you can put x equal to 5 in the volume function and get the maximum volume. Now, this was something as we called as a regular, very conventional, very traditional box problem, well tested, well discussed. Another of the possibility which is important from exam point of view as well is where we talked about inscribed solids. Largely speaking, there are three cases that you need to be familiar with. Case where a cylinder is inscribed in a sphere, a cylinder is inscribed in a cone, and the third possibility, a cone inscribed in a sphere. Given solids, certain solids are inscribed in it, we want to find those dimensions such that the inscribed solid has maybe maximum surface area or maximum volume. In today's lesson, we will discuss one of those possibilities. Note down the question, and as I said earlier, statements are long, but these are the questions from your NCERT textbook. The question says, show that the volume of the greatest cylinder which can be inscribed in a right circular cone of height h and semi-vertical angle alpha is 4 by 27 pi h cube tan square alpha. Now, what do we mean by a cylinder inscribed in a cone? Take a look at this picture. Here we have a cone. Cone is given. Why? Because its semi-vertical angle, which is the angle between the height and slant height, is given to us. So, given would mean it is fixed, constant. Therefore, the height and radius and slant height of the cone are fixed. It is only the cylinder which is inscribed is changing its dimensions. So, there is a possibility that you can have a cylinder like this inscribed, that is the surface, as one look at the rim of the circular top is touching the surface of the cone, or you can have a cylinder which is taller, thinner, inscribed in that cone, or shorter but broader inscribed in the cone. There could be many such cylinders that can be fitted in. We want to find the one which has the maximum volume. So, let us consider this situation and let us start deciding unknowns and knowns. Let h be the height of the cone which is given to us, r the radius of the cone again given to us, given to be underlined and understood as constant, they are not changing. Let the height of the cylinder, that is O dash O distance, be y, which is varying, as you saw in the 3 possible positions earlier. Same would be the radius of the cylinder, again changing quantity, varying quantity. These are the dimensions of cone and the cylinder. The h and r are given, y and x are changing. The key to this problem is to figure out a relation between y and x such that the volume of cylinder can be written as a function in one variable. In this case, the relation comes through similar triangles. The triangle AO dash D is similar to triangle AOC, and therefore, the corresponding sides are proportional, which means AO dash upon AO would be same as O dash D upon OC. Replace them with their measurements. In this case, here AO dash is same as AO minus OO dash, and therefore, it is h minus y upon h equal to x by r. This gives rise to y in terms of x. Again reminding you, h and r are constants. So, y is now in terms of x, and therefore, we are ready to write the volume function. Volume of cylinder is nothing but pi square of radius into the height. So, in this case, it is pi x square y, and so replacing y in terms of x using what we derived earlier, I get a function as pi times h x squared minus h by r x cube. This is a function which we need to now maximize. So, now the procedure is mechanical. Find the derivative, put it equal to 0 for maxima or minima. In this case, we get two values of x, 0 and 2r by 3. We reject 0. Why? If x is 0, that means there will be no cylinder. So, we focus only on x equal to 2r by 3. Is this a point that gives us maximum volume can be only verified through the second derivative test. So, I find the second derivative, and when I put x equal to 2r by 3, we get the second derivative negative, which confirms that V is maximum when x is 2r by 3. When x is 2r by 3, what would be the height? Again, using the relation we derived earlier, y turns out to be 1 by 3rd times the h, that is the height of the given cone. This could also be the question in its own. You may have to verify or show the volume is maximum when the inscribed cylinder's height is 1/3 the height of the given cone. In this case, we want the maximum volume. So, what is the maximum volume? Putting x as 2r by 3 and y as h by 3, we get 4 by 27 pi r square h. But that was not the question. we wanted to get an expression in terms of alpha. So, let us relate h and r in terms of alpha. Plain trigonometry tells us nothing but r by h is tan alpha. So, I can always replace r by h times tan alpha, and therefore, the maximum volume of inscribed cylinder turns out to be 4 by 27 pi h cube tan square alpha, and that is exactly what the requirement of the question was. So, starting with known, identifying what you want to find and relate. In case you have two variables, relate the two variables to each other, so that the function which you need to maximize or minimize becomes a function in one variable. Use the idea that for maxima or minima, derivative must be equal to 0. Once you have got the critical points, use the second derivative test to verify whether that point is a point of maxima or minima, and that is usually the standard procedure for all of the word problems. Of course, the difficulty level does vary, and for that all you have to do is practice. So, today's lesson was on maxima minima word problems. Hope you have enjoyed it and you have gained something out of this. See you in our next series.